Okay, hey guys. So I am going to now run through the three examples that I left for you. We're going to be using this sheet, which spells out the example. I'm going to be using the Excel spreadsheet, and I'm also going to be using this document, which is also called class examples for you. So this is what you're going to open when you want to go over this. The last video I'm going to do is I'm just going to go into SPSS. Okay, so the first example is the boring example from our textbook. Let's see what I did in the Excel spreadsheet. So we list all the subjects, we list the before, we list the after, and here is the column that we really care about. We care about the difference column. So it's kind of nice. We don't have a lot of confusing. We don't have to go back and forth between the before and after scores. I'm just centering these. My brain works that way. So you take the sum, the count, the mean, the variance, the standard deviation, and standard error of each of these, of the difference. And then we don't have to worry about the before and after scores that much anymore. We go into the document. Now I decided, just so that we had a lot of good examples of different types of tests, I'm running this as a one tail in the positive at 0.05. So we set alpha at 0.05. It's a one tail. There's 8 degrees of freedom with a dependent test. So we have 9 pairs, which we saw here. There's 9 pairs of scores. That was right on the slide too. 9 pairs of scores. So our T critical, again, we get that from our T table, is positive 1.860. Run the study. Our T obtained is the difference. So it's just the difference between the two scores. Again, that comes from the mean here. Mean difference is 0.22. We divide it by the standard deviation of the difference over the square root of n. So we divide it by remember, this is standard error. And we wind up with a T obtained of negative 0.312. So this is an easy example, right? Because we failed to reject. So there's no difference. At this point, remember, when you fail to reject, you stop. Okay, so let's go on to the second example. This is an Atkins diet. So this is, again, a very typical example that we look at when we're teaching dependent means. It's easy to remember the before and after of it. Atkins diet advocate believes that an all-fat diet significantly reduces weight. So this was a big thing back a few years ago. So this advocate takes her current 7 clients and weighs them before and after. They're on the diet for 6 months and compares their body weight. And here's the data that we're presented with. So we have 7 subjects. Here's their weight before, and here's their weight after. And we go to the class examples of the calculations for this. And here's what we do. So there is a weight beforehand and there is a weight after for every single participant. Remember, these are dependent. We have 2 scores for every participant. And we wind up with a mean of negative 15, the mean difference. You'll see some people lost, some people gained. So this is the weight before minus the weight after. And then this is the data that we want to use when we are doing our calculations. Let's go for it. So I'm running this as a 0.01 one-tail test. I believe there's nothing there. This should be less than. Sorry about that. So T critical is degrees of freedom n minus the number of pairs minus 1. 7 minus 1. Again, where did I get that from? We have 7 pairs. So we have 6. So our T critical at 6 degrees of freedom at 0.01 equals negative 3.14. We run the study. We calculate. So what are we calculating? We're calculating a test statistic here. So it's the difference of what we believe the difference will be minus 0. So it's what the difference that we obtained minus 0. So it's negative 15 over 4.88, and that turns out to be negative 3.074. Now, again, I spelled this out for you. This is the standard error of the mean difference, okay? So it's the standard error of the difference, 12.91, right here, over the square root of the number of pairs. You get 4.88, and you put that up in the denominator of your test statistic. So we compare the critical value of t, which is 3.14, to our calculated value of t, 3.074, and we fail to reject. So what then I did is I said, okay, well, let's, as a teaching example, let's move alpha. So here we're going to change alpha to 0.05. Now, again, you would not do this in regular practice. So alpha is now 0.05. When you change your alpha, your critical value changes. So we're going to bring our critical value down now to negative 2.447. Remember, it's plus or minus. In the table, we take the negative because we're running it as a one-tailed test. And here, now we can reject. And why does this happen? Because it's easier to reject at 0.05 than at 0.01. So at 0.05, now we can do our confidence interval. So confidence interval is the difference plus or minus the standard error and the critical value. Couple notes here. So we run a two-tailed alpha equals 0.05 confidence interval. We can run a one-tailed, but we always get a confidence interval. We get the two-tailed value. We do not use the one-tailed value. So it's negative 15 plus or minus 4.88 times 2.447. This is from the table, and this we calculated. And we already did that up here, 4.88. Okay, so our confidence interval is negative 15 plus or minus 11.941. We then have a confidence interval around the mean difference that we would experience in the real population. So we would say and interpret this as the mean difference in the population is going to be somewhere between negative 26.941 and negative 3.059. Now, what does that mean? Remember, interpretation is really important. That means that in the population, we can expect subjects who are on the Atkins diet to lose between 26 and 3 pounds and some change. And then we have Cohen's d, practical significance, meaning is the standard deviation, is the difference between the means large enough for it to really be practical and make a difference? So here, the difference, now this is where you need to really pay attention to your calculations. This is the standard deviation of the difference. So this is the standard deviation of the difference right here, not the standard error that we use in the test statistic. This is the standard deviation of the difference. So it's negative 15, again, the mean of the difference, over 12.91, the standard deviation of the difference. And our Cohen's d winds up to be 1.16. And as we know from the table that we saw in lecture slides, this is a large effect. So we would say that there's a significant difference and it's practical and it's large. So that's example number 2. And then I laid out, I'm going to go over this again, but I laid out for you how I set up, just so you have another example, how I set up the variables and the data here. And then you have the directions and what the printout looks like. And we're going to go over those as well. Okay, two sample dependent two-tail reject. You know how much I love to put up notes. Okay, a major oil company would like to improve its tarnished image following a large oil spill. Its marketing department develops a short televised commercial to see if and how a video changes a participant's attitudes about the company. The execs select a sample of n equals 7 participants. People's attitudes about the company are measured with a short questionnaire both before and after viewing the commercial. So here's what happened. This oil company had a large spill, and now they want to improve their image after wrecking the local environment. So they brought in 7, so they made a video of how great the company is. They brought in 7 people, and they took their attitude about the company before and their attitude about the company afterwards. And here's what happened. So we don't know. We just want to know, does the video change? We don't know which way it's going to change. Obviously, we're hoping it's in the positive, but they didn't say that. So H sub O and H sub A. We have our alpha. I set it at 0.01. Degrees of freedom. There are, I forget how many pairs. Here we go. 7 pairs. So our degrees of freedom, our critical value of t with 6 degrees of freedom at 0.01 is plus or minus 3.707. We run our study, we get our test statistic, and we compute a test statistic of 4.17. So where did these numbers come from? This is from the spreadsheet, 5.29. This is the mean of the difference. And then this is the standard error. So this is the standard deviation of the difference over the square root of the number of subjects. And then you compare. And then we say we rejected, the video made a difference in attitude. So then I also, oh, this is a duplicate. Sorry, I copied that twice. So here's the oil company again, and here's their confidence interval. So it's the difference plus or minus the standard error with a critical value. And I did a two-tailed confidence interval this time. So at 0.01, remember, always use the two-tailed value of a confidence interval. So we say, and I think I'm missing, no, I'm good. Okay, it's 5.29 plus or minus 1.27, 3.707. Here's your critical value at 0.01, two-tailed. And this is your standard error, which we computed. Well, back here, it would be in here. And it's also on the sheet. So we wind up with 0.583. So the average attitude of change is going to change somewhere between 0.583 and 9.997 points on whatever scale of attitude that they're using. The most important thing also, don't forget with confidence interval, I shouldn't say the most important, but one of the big features of interpreting a confidence interval is also saying you're 99% confident that the actual difference before and after difference is between 0.583 and 9.997. Okay, and then the Cohen's d, again, this is the practical significance. So we get 5.29 over 3.335. Where did I get those numbers from? It is the difference, just the mean difference, over the standard deviation of the difference. Remember, we don't use standard error with Cohen's d. Okay, so that's running through the three examples that I left for you. Now I'm going to take a break, and I'm going to come back, and I'm going to go through the SPSS for each one. That'll be the last video that I do.